Hello, my name is Christophe de Bruyne and welcome to the second lecture on Open Information Systems, and in this lecture we will cover both RDF and RDFS. RDF stands for Resource Description Framework and is a way to represent things as resources on the web, and RDFS is a very simple schema language built on top of that data model. Because we have a lot to cover in both RDF and RDFS, Lecture 2 will be split into two, with this one focusing on RDF. Now, before we continue, let's go back to the problem we tried to tackle. Now, quite often you will find that whenever systems need to interchange information with one another, they will create bespoke pipelines or translations or mappings and whatnot, which is very difficult to maintain. As you can see here on the left, a fifth system tries to join the ecosystem, resulting in 4 additional translations, links, mappings, and whatnot that need to be created and maintained. So the problem is n times n minus 1, where n stands for the number of systems, divided by 2. And here we have about 10 links. Now, we can significantly reduce that the complexity by introducing an artifact in the middle, which represent the shared concepts and relationships, and that we call an ontology. Remember, that was the topic of the previous lecture. Now, in such an environment, whenever a fifth system needs to join, then only one mapping towards the ontology needs to be created and maintained. So how do we create these ontologies? Well, we will avail of a couple of technologies covered by the Semantic Web Stack. Again, as in the previous lecture, multiple such stacks exist, but the gist remains the same. They propose a layered approach where we have standardized technologies building upon one another. The things that we will cover in this lecture are RDF and RDFS. So in RDF, we will see a very simple data model for representing statements about things. Now, those statements need to be stored somewhere. And how are they stored? Well, we will see both a XML representation of RDF and a other more terse one called turtle, and in these formats things will be identified by RAIs and they will be stored using a particular character set. Now, the data model only tells us how things and their relationships are represented, but it bears very little semantics. So we will also see a very simple extension to RDF called RDF Schema, allowing us to create vocabularies in terms of type hierarchies, role hierarchies, and the domains and ranges of properties. So let's start with the resource description framework. Now, in this particular part, we will familiarize ourselves with both the RDF XML and turtle serialization of the RDF data model. If you're not that knowledgeable in XML and XML schema, don't worry. The form is useful for context and terminology. You will see that the latter is often adopted in practice. So the Resource Description Framework, or RDF, is not an ontology language, but a data model, even though RDF provides you with constructs that make you think it's an ontology language. RDF is a W3C recommendation, which means it's a standard, and it was first published in 1999, so it's been around for a while. RDF is designed to be read by computers and not by people, and it is used to describe resources on the web. And in order to describe resources on the web, we need to identify and refer to those, and we do so by using URIs. Now, RDF XML is just one way of serializing or storing RDF. Other serializations include turtle and n3, with n3 being a superset of turtle. And we also have RDF serializations that support named graphs, such as nquads and trig. Important, however, is RDF is the abstract data model, and RDF XML or turtle are just ways to represent and store statements in RDF. So RDF XML is not RDF. RDF XML is just a way of serializing RDF. So let's dive into the deep end of the pool with this example. This is an RDF XML document that will describe my website. Now notice that inside this document I have declared the RDF namespace. That RDF namespace contains the, let's call them predicates that we'll be using throughout a RDF XML document and later on as well other serializations. I use this namespace to denote the root of my RDF document, which is only necessary for RDF XML. So we state that the document starts there and ends there, and it will only contain descriptions of things. Now, I will be describing my website, so I will start by creating an RDF description, see how that description, that concept is declared in the RDF namespace. So I create a description of my website with this particular URI, and I will be stating the following things. That thing has a title, Christoph's homepage, and that thing has the topic, semantics. Now, title and topic has been declared in a different namespace, example, and I will be telling a little bit more about that later on. Now, I have a description about a thing that contains two statements. HTTP www.christophdebruine.be has the title Christoph's homepage and has the topic semantics. So these two statements are triples. They're triples because they contain three things: a subject, a predicate, and an object. And that is basically the a atomic statement in the RDF data model. So here's the equivalent, one of the equivalent representations of the RDF XML in RDF Turtle. And in this particular example, I declare both RDF as a namespace and our example namespace. The example namespace wasn't necessary for this particular document, but then that would have meant that we would have written the URIs of both title and topic in full, which is not really convenient and creates additional overhead if we were to exchange these documents. Now, in this particular example, we have the two statements as separate statements in the Turtle document. Each statement consists of a subject, predicate, and a object, and ends with a period. Now you can see that both statements starts with the same subject, so there's a little bit of overhead there. Can we reduce this? Well, yes. So yes, Turtle allows us to be a bit more terse. So here in this example, equivalent document, we again have two statements, but we avail of a little construct to avoid redeclaring the subject of a statement. So here we have our thing, which has HTTP www.christophdebruine.be as the subject. It has a particular title called Christoph's homepage, and then rather than a period, I avail of a semicolon to state I will tell something else about the subject, which is the topic being semantics. And now I end that description with a period. Now, I already stated that the predicates from RDF are declared in the RDF namespace, but where do title and topic come from? Well, ideally, if you were to follow these predicates, then you would see them declared in another document here. So if we were to do an HTTP get of the namespace, hopefully we get something that tells us something about the predicates we use in our RDF documents. So here we can see in this particular RDF document that title is declared as being an RDF property and topic is also declared as being an RDF property. Now there's very little semantics, and I haven't elaborated on the example. All of that will follow in due time. In the previous slide, we've seen that predicates or properties need to be declared in a namespace and therefore must have a URI. This is an opportunity for me to elaborate a little bit more on what accepted between quotes values are for subject, predicates, and objects. Here you can see that a subject may be either a resource identified with a URI or a resource without a URI, also called as anonymous resources or blank nodes. The predicate must be a resource with a URI, I've seen on the previous slide. An object, however, can either take the shape of a resource, blank node or named, or a literal. So you cannot use literal values as the subject of a statement. So in RDF XML, whenever you use a property name, well, then you need to qualify it with a namespace prefix, and that namespace prefix must be associated with a schema that has been declared here above. RDF is used to describe things on the web. If we want to describe something that already exists, we will avail of RDF About to refer to that thing. If we need, however, to create a new resource as a named node inside a document, we will be using RDF ID to create a new thing inside a RDF document. So here we have a simple RDF XML document in which I declare the base to be http://www.example.org/example. The base URI is used to resolve relative URIs inside the document. For instance, if I were to have a named node foo and I have no information about its absolute URI, then it's considered to be a named node declared in that base. So the absolute URI of #foo would be http://www.example.org/example #foo. Now inside that document, I create a new resource and I will be using RDF ID. So I describe Christoph declared as a new node inside that document. Because I create a new node, the node's name will be #Christoph. And I state something about Christoph. It has a name, Christoph de Bruine. Now I will be describing something about that thing that already exists. So I describe my website, description, RDF About, resource that already exists, and I state it has an author, and that author is a resource, and now I can reuse the one that I've declared earlier. But now I have to refer to it by its relative URI with the fragment #Christoph. We now know that this is a named node relative to the base URI, and we have declared that the website is authored by that thing, and that thing has another description over there, which states that it has the name Christoph de Bruine. This notion of RDF About and RDF ID does not exist in RDF Turtle. We just use URIs, either absolute URIs, relative URIs, or via namespace prefixes. So this is the same example where I declare Christoph, which is a named node inside http://www.example.org/example to have the name Christoph de Bruine. Then I declare that this thing with the URI http://www.christophdebruine.be, my website, has the author, the resource with this particular URI, which is the same as the one above. And this is how a RDF agent knows that this is the same thing. Now, in this example, you might have noticed that you can have properties that have as a value either a literal or a resource. And this is how we will be creating graphs. So over the years, I've noticed that people dealing with RDF, especially at the beginning, struggle with URIs, and that's why I've decided to spend a little bit more time on that. So relative URIs are resolved relative to the current base URI, and the current base URI of an RDF document is usually its location. So if you store your RDF document under the C drive, the base URI is the C drive. Now, because you will oftentimes store that document elsewhere, and people might be able to download it, yet you want to ensure that the URIs do not break, you can provide directives that overwrite the base URI. You can inform the parser that the base URI of a particular document is something else. You do so with the XML base directive in RDF XML or the add base directive in Turtle. So when you publish your ontology and I download it and I process it, I still know that the URI, the relative URIs, are with respect to the location of the ontology, not with respect to the location of the location where the file has been downloaded. Now, here are the various directives and their interactions for RDF XML and Turtle. Now, assuming that I have provided an XML base directive for my example, notice that base directives never end with a fragment. That shouldn't happen, right? So here I have my base directive, http://www.example.org/example. And in RDF XML, if I were to declare a name node foo, then that name node will be a name node with a fragment declared in that relative to that base URI. If I were to use RDF about and I provide a fragment, then it will be describing something as a named node in that base URI. However, and this is where a lot of people in the beginning make a mistake, if I were not to provide a fragment, it will be considered a path, not a named node relative to that base URI. So it will be concatenated to the base URI with a slash. And that is where a lot of mistakes are made. Now, similarly in Turtle, now remember in Turtle we don't have this notion of RDF ID and RDF about, but if we were to declare our base in a similar way and we use a resource and provide a fragment, then it will become a named node inside that base. But if we don't provide a fragment, then it will become a path attached to that base URI. Now, hopefully you will bear that in mind when you are going to write or process your RDF. So from now on, I might be omitting the root element of RDF XML documents just to keep them simple, but they have to appear in order for them to be valid RDF XML documents. In this example, I usually ask students to point me things that they see, they deem strange with the knowledge they've gained so far. And usually they might discover that I have two descriptions about the same thing, and that is fine. You can scatter descriptions about things inside a document and even across documents. A computer-based agent that is capable of understanding RDF knows how to merge those. The second thing they might notice is that in two different descriptions, I have the same statement. I have the property title with the exact same value. Again, that is fine. For a computer-based agent that understands RDF, whenever it encounters for a particular thing the same property with the same value, it is considered a duplicate. So by merging these two descriptions, there is only one title. Now, had the agent encountered another title, with the same value but with a different language or a declaration of a language, XML lang equals English, for instance, then a title Christophe's homepage without a language tag and a title Christophe's homepage with a language tag would be deemed different, and then there would have been two titles. The third thing they might notice is that I have a description without a URI. This is a thing without a name, and that we call a blank node. Blank node are resources without a URI, and we will cover them later on in this lecture. Now, blank nodes can also be represented in RDF Turtle. The inline declaration of a blank node is done by means of square brackets here. So here we state that the thing with URI http://www.christophedebruyne.be has the author, the unnamed thing that has the name Christophe de Bruyne. Now, we can also declare our own blank node identifiers, which allows us to refer to blank nodes from various places inside one Turtle document, not across Turtle documents. So here we have our website, or my website. I declare its author to be a blank node, and I provided an arbitrary blank node, internal blank node identifier, foo, and I reuse that foo to say something about that thing, and I state it has the name Christophe de Bruyne. Now, you might wonder, is it really necessary to create and manage your own blank node identifiers? And the answer is yes, because it may happen that your blank nodes appear as subjects and objects in your RDF document. So in this particular example, I have created descriptions of my three cats, Victor, Bettina, and Gaston, and they're all owned by something, and that something is being described as having the name Christophe. Now, in RDF XML, you can also provide blank node identifiers for your blank nodes, and you will be using RDF node ID, which is different from RDF ID in RDF XML. Remember, RDF ID is used to create named nodes in your RDF XML documents. RDF node ID is used to create blank node identifiers. Now, in this RDF XML example, we have described the same thing. We have a Bettina. Bettina is owned by something that has no identifier, but it's been given a node ID with the name Christophe, and then we can reuse that resource via its node ID to describe Victor and Gaston, their owners. So RDF XML can be quite verbose. That's why the specification provides you ways to reduce the overhead with syntactic sugar. So property elements, for instance, can be converted into attributes, provided that they only occur once for a particular description and their literal values, no resources. So in this particular example, I have a description of my website and it has the title Christophe de Bruyne. Because it only has one title and its value is literal, I can transform that into an attribute rather than an element. The same for the property topic. Now, next to declaring relationship between things and their values using properties, you can also declare the types of things. And things, resources on the web can have more than one type. Now, this is arguably something that belongs to an ontology language, whereas RDF is supposed to be a data model, but it's there and we can avail of that. So in this simple example, I declare my website, well, the thing with that URI, to be of the type a web page, and that web page is supposedly a node inside an ontology that I refer to with RDF resource. Now the same thing can be done with RDF Turtle. I again declare the ontology in the namespace example, and I declare the RDF namespace using the namespace prefix RDF, and I declare that thing with that URI to be of RDF type web page. Now, because type declarations happen so often, in RDF Turtle, they've created a shorthand for that, which is A. So you don't need to declare the RDF namespace if you only use it for RDF type, and you can just avail of the letter A to state that thing with that URI is a web page. Luckily, in RDF XML, there's also syntactic sugar. You can use the value of RDF type directly as an element name. So in this particular example, we know that the thing with that URI is of the type web page, and I will be using this resource in that namespace to declare it as an element name here. So I have an instance of a web page with that URI. It has a title and a topic. Now notice that I have a namespace prefix here. So that means that that namespace prefix must be declared in the RDF XML document at the top. So we assume that this is the case and that it refers to the resource containing our ontology. You have two types of literals in RDF. You have plain literals and typed literals. Plain literals are strings that may have an optional language tag. Typed literals are strings that have a data type tag, and those data types are usually XML data types coming from the XSD namespace. Because language tags have no meaning for typed literals, they are ignored when you use them together with a data type tag. Here's an example of RDF XML where I use a couple of these constructs together. I'm describing something with the node ID Christoph, and I state that that thing has the name Christoph using the XML lang attribute en, and en stands for English. So this is his name in the English language. The second statement uses the same predicate name but without a language tag. For RDF, those two names are different because the one uses a language tag and the other doesn't. In the third statement, I say something about his height, which is 171. I know that this is a number, so I declare its data type to be XSD integer, and I use the RDF data type attribute to do so. The fourth statement states again my name, but now I use a data type rather than a plain literal, and I state it's of the type string. Again, Christoph as a string is different from Christoph as a plain literal. Here's the equivalent RDF document in Turtle. Here you can see I use the XSD namespace, and you see the syntax used to annotate literals with data types and language tags. For a data type, we use two carets next to a string to denote its data type. So here we have the height being an integer of 100 with the value 171. And here we have all the names. This is again a shorthand for stating that this particular resource has for that particular property 3 values because they are separated by commas. But here that thing has 3 names, one being a string Christoph with the data type XSD string, a plain literal without a language tag, and a plain literal with a language tag for the language English. So far we have seen that in RDF we can describe things, and things are either anonymous, they don't have a URI and therefore they're blank nodes, or they have a URI, so they're named. And things can have relationships with other things via a property, or a relationship with literal values via a property. Now, the RDF recommendation also provides other types of constructs that we will cover. Now, one of them are RDF containers. What are RDF containers? RDF containers are sets of things. Now, an RDF container can be extended. Once you have a container, you can add elements to it. So they are not closed. Not closed. We will see later on another type of construct which you cannot change once it's declared. Now, before I continue describing the different types of containers, it's important to note that their use is often discouraged, but some vocabularies, especially in the library domain, still avail of those. So it's worthwhile being aware of their existence and knowing how to use them. Now, the reason why they're discouraged is that they make querying a little bit more challenging, and we will see a couple of examples later on. Now, the three types of containers are bag, sequence, and alternative. In a bag, all the elements, their order has no importance, and they can also be a mix of resources and literal. Actually, that's true for all of them. In a sequence, the order is of importance. And in an alternative, you provide a list of resources or literals that represent alternatives for the value of a property, which is quite challenging if you were to query over that. Now, let's go over to the first type. So here we have an example of how we can use RDF containers. In this example, I will be showing you how I adopted 3 cats. So here you have me, and I adopted a bag of cats. And inside that bag, I have 3 list items, one for each of my cats, Victor, Bettina, and Gaston. Things become a little bit more tangible, hopefully, if you were to represent that in RDF Turtle. So in Turtle, we will see that I actually adopted an instance of the type bag, and that instance, that thing, has no URI, so it is actually a blank node. And inside that blank node of the type bag, I have 3 things that represent my cats, Victor, Bettina, and Gaston. Now don't let those numbers fool you, because in a bag, order has no importance. Now, key is to understand that there's a difference between Christoph adopting a bag of cats and Christoph adopting 3 times a cat. So I adopted Victor, I adopted Bettina. Obviously they're named nodes, so there's a hash here, and I adopted Gaston. So this is where things get a little bit more challenging. If you were to be a user, you wanted to know who adopted what. What do you want to get returned? Do you want instances of cats? Do you want instances of bags? A mix or both? Well, obviously a mix of both would make understanding and interpreting the results a little bit more challenging. That's why people usually encourage the use of ontologies and ontology design patterns whenever you need to deal with containers. Now, we covered bags. What about sequences? I will continue with my example of adopting cats. we already discussed briefly the challenges between representing containers or representing things separately. But in this particular example, I will now adopt a sequence of cats, and in RDF Turtle, so here only the type of my container changes, and the same is true for RDF Turtle, where RDF bag is replaced by RDF sec. Now here the number does have an importance. Victor is the first in that set, Bettina is the second in that set, and so on. The meaning of that order, however, is unclear. Maybe I adopted Victor first, maybe I prefer Victor over Bettina. We don't know it yet. The only thing that we are certain of is that Victor is the first element in that container and Bettina is the second. A little bit more challenging is alternative. Now I will be describing my cat Bettina, and Bettina listens to alternatives. So depending on that predicate, you have a value to choose from a set of alternatives. So Bettina listens to Bettina, Cocotte, or Bouboule. In RDF Turtle, nothing really changes. Again, the only change is the type of the container. And again, we have those numbers who do not really mean anything. The only thing we know is whenever you look for that particular predicate, you have several alternatives to choose from. Another construct that RDF provides are RDF collections, also known as lists. So we've already seen that RDF containers can be extended. Why? If you have a reference to a container, you can add elements to it. This is different. In RDF collections, you can't add additional things. Once a collection is declared, it's immutable. So that is important to know. Collections are immutable. Now, here's an example, and bear with me, it seems complex, it is complex, but we will see tricks to make it easier to write down. So in this particular example, I will describe how I look after my cats. So I, Christophe, am looking after a list of cats. So that list is declared as being a blank node with node ID C1. So I'm looking for that, and I see that that blank node is described here. And the first in the list is Victor, and the rest is declared in another blank node here. And if I look at C2, the blank node with blank node identifier C2, I see that the first is Bettina, and the rest is declared elsewhere. And if I were to look at that resource C3, I see that the first is Gaston and then the rest is nil. This looks as follows. So I have Victor, and then this one points to another construct. This one is Bettina, and this one looks at another construct. This one is Gaston, and this one is empty. Now, people familiar with computer science, they might recognize the terms first, rest, and nil, because that comes from a computer programming language that was very popular in the artificial intelligence community called Lisp. Now, as I said, this looks very convoluted, but there's an easier way to model lists in RDF XML. So how can we do this in a less verbose way? Well, here we have me looking after, this is the predicate, after my cats, and notice that usually you are only allowed to have one value for a predicate or property, but here I have 3. In this case, it does work because I inform the RDF processor that this predicate should be parsed as a collection. And you can do the same thing with containers. Now, by doing so, it will know that all these values have to be gathered into a list. In RDF Turtle, it's even easier. You only need, you need to declare lists with parentheses. You open a list with the open parentheses and you close one with the closed parentheses. So here we have Christophe looking after Victor, Bettina, and Gaston as a list. One limitation of RDF is that it only supports binary relationships, being a relationship between a subject and an object via a property. What if we want to model ternary relationships, or we want to add weights or confidence intervals to properties? Well, that's not possible unless we consider that property to be a resource. Now, here's an example. I want to represent Bettina's weight as a combination of a value and a unit. So here I have my description of Bettina. I state that she weighs 6.8 as a value, kilograms as a unit. Now remember, property can only have one value, and here I have 2, which is not possible unless I instruct the RDF processor to parse this property as a resource, and then it will work. This will become a resource with 2 properties, being RDF value and unit. Now, graphically, this looks as follows. I have my cat, Bettina. She weighs something that has no URI because it's a blank node, and that something has the value 6.8 and has the unit dBpedia kilogram. In RDF Turtle, you clearly see that this becomes a resource, and an anonymous resource at that. This Bettina weighs something, and that something has the value 6.8 and the unit dBpedia kilogram. Now, you might be wondering, where does RDF value come from? Well, RDF value is provided by the RDF recommendation. It doesn't really have any semantics or a meaningful connotation, but it is encouraged to use RDF value to denote structured representations of value, because it provides you a common property to achieve that. So they aim to reduce semantic heterogeneity for structured representation of value by providing a predicate for that. So if everybody uses value to represent ternaries turned into resources, well, part of the problem is already solved. So to summarize, RDF only supports binary relations, and a predicate can only be applied to exactly one value, as we've seen before. If we don't provide a parse type resource, the parser will generate an error because a property can only have one value. Now, the RDF parse type resource instructs the parser to generate a resource and attach all values as attributes of that resource, as we've seen in the previous example. So we've already seen that the subject of one statement can be used as the object of another statement, and that allows us to create directed labeled graphs. In this particular example, I exemplify that thing once again. So here I have a description of a person, and that description has the first name Christophe and works on another thing. And that other thing is described elsewhere as being something with the title Open Semantic Cloud for Brussels. That was one of the projects I used to work on. Now, if you look at that, you can see that Open Semantic Cloud for Brussels is used both as an object of the statement Christophe works on, that project, and is also used as the subject to declare the title of the project. Now, RDF structure can, unlike XML, be broken down and distributed, and this is quite important, in the same document or pointing to another document. And joining of the different resources using lazy loading and the URIs can be done in order to merge the different graphs. Another challenge in RDF is reification. Reification is about making statements about statements or second order logic. Here we have an example. We have a relationship between the song Love Me Do and the Beatles being performed by, so we have the song Love Me Do performed by the Beatles, and I give that relationship a ID S1, and I will be using that ID to say something about that relationship. And what do I say about this? Well, I have a description of a person with the node name Robert, and I state that that thing likes that performance. How does that look like graphically? Well, we have here our statement Love Me Do performed by the Beatles, and I give it the node name S1, and Robert likes S1 being that statement. Here we have the same example using RDF Turtle, and here the challenge with reification will become more apparent. We state that Robert likes something, and that something is a statement with an object being the Beatles, a predicate being performed by, and the subject being Love Me Do. Now, RDF statement and the three properties are all declared in the RDF namespace, which has been standardized by the W3C organization. And this is the same example. We're making a statement about a statement. We state that Robert likes the performance Love Me Do by the Beatles. However, now you see that these seemingly two statements, and they looked seemingly as to like two statements in RDF XML, are turned in about 4 to 5 statements internally. We have the statement of Robert liking something, and that something has an object, a predicate, and a subject. So we already have at least 4 statements. Now, the fact that something is also of the type RDF statement might be included explicitly or not. So these two statements get turned into 4 or 5 statements internally. And I hope that you now see how this can create unforeseen circumstances. If I ask the endpoint, what does Robert like? Then I will get an instance of a statement rather than the relationship. I won't get that. So here we have the same example. These two examples of RDF Turtle are equivalent, but in the one I don't avail of the base directive, and in the second one below I do avail of the base directive. And you can see that rather than availing of the namespaces for referring to Robert and the statement, I use the base directive and use relative URIs to refer to those. I just wanted to provide another example of how one has or can use base URIs in RDF documents. Now, to conclude, what did we cover in this first part on RDF? Well, we've seen that RDF is an abstract data model allowing for the creation of distributed knowledge on the web. We've covered mainly 2 serializations, being RDF XML and Turtle. We've seen different types of resources. We've seen blank nodes, which are anonymous resources, and we've seen named nodes where resources are provided a URI. The basic knowledge building block in RDF is subject, predicate, object, where subjects are resources, either named or blank. Predicates must have a URI, they must be named resources, and objects are either named or blank resources or literal values. When resources are used as both a subject and a object, you create directed labeled graphs, and descriptions can be scattered within a document and also across different documents. We've also seen that RDF allows you to declare types using the RDF type property, and we can also avail of containers and collections. We've also covered some limitations of our RDF, namely those to do with reification, making statements about statements, and non-binary relationships when where we have to transform those into resources because RDF only supports subject, predicate, object. So we've seen how we can deal with those limitations in RDF. Now, here are a couple of references. In this particular lecture, we mainly covered things to do with RDF, RDFS, and XML Turtle. I will also provide a couple of exercises, and until next time when we will be covering RDF Schema.